All right, take a look at section 2-4. We're on page 45 in your book. The title of this section is Continuity and Discontinuity. Our objective here is given a function determine points of continuity and discontinuity. We've already looked at the formal definition of continuity and what it means for a function to be continuous at a point or on some interval. And we've looked at several examples of functions that have points of continuity, points of discontinuity, and we've worked with that. For this part, we're going to take a look at one of our limit theorems that we've skipped over at this point. And that's because, as we'll see in a minute here, this limit theorem requires us to know something about continuity. So now that we've formally defined that and we know what it means to be continuous, we can talk about this limit theorem. This is the limit of a composite function. And before we talk about the theorem, let's remind ourselves what we mean by a composite function. If you have something like y is equal to f of g of x, something like this is what we call a composite function. In fact, we even name the two parts of this. We call g of x our inside function, and we call f of x the outside function, or f here our outside function, are the names we give to those two parts. Again, what this means is that you're going to take some value of x and you're going to plug it into the inside function. That's where x is applied first, as you can see from that statement there, f of g of x. X gets plugged into g first. And then the result from that, that is the output from function g, we take that and plug it into function f. So we're not plugging x into function f, but rather we're plugging g of x into function f. And that gives us some result. So that's what we mean by a composite function, made up of an outside function and an inside function. And we work from inside out. Start with the inside function and then work your way out. All right, so here's what the theorem states. There's two conditions for this theorem, so you got to make sure that you meet both of these conditions before you use the conclusion here. The first condition says that the limit as x goes to c of g of x is going to be our inside function here. If that limit is equal to L, now two things there. First of all, the limit has to exist is what that statement's saying there. That's because it's equal to some value. And the name we're giving that value is L. So we're stating two things with that first part there. The limit has to exist, and we're going to call that L. The second condition is dealing with the outside function, and that is function f has to be continuous at x equals L. Notice, by the way, with that we are looking at the limit of the inside function and using that as our place that we're considering continuity at. So it's not x equals c that we're worried about continuity at, but rather at x equals L. And that's because of the fact that this is a composite function, so we take the result of the inside function and we plug that into the outside function. So we got to check for continuity at L. If you meet both those conditions, then here's how we can find the limit of this composite function. That's what the conclusion states here. Then the limit as x goes to c of f of g of x is equal to f of the limit as x goes to c of g of x. In other words, you can take the limit of the inside function first and plug that result into function f. Now up above there, and with the first condition, we called that limit L, so that's the same then as just saying f of L. This turns out to be a very nice way to find a limit of a composite function, as long as you meet both conditions. And that will be critical. You got to check for these two conditions first, then we can apply the theorem. However, we're going to see functions where we don't meet these conditions. So then the question is, well, how do we deal with those? And that's what this note down below here is for, to help us out with that. If you don't meet those two conditions, if the two conditions are not true, it could be that you meet one of them but not the other, or it could be that you don't meet either one of the two. Doesn't matter. If you don't meet both of those conditions, then you're going to have to use one-sided limits to help you evaluate this. And we'll see some examples to illustrate how to do that, but we'll consider what's happening from the left side, we'll consider what's happening from the right side, and see if those two give us the same result of this composition. And if it does, we have a limit. If it doesn't, we don't have a limit. All right, so let's take a look at a few examples here. Start with example 1. For all three of these examples, we're going to use these exact same graphs here. Function f and function g will be the same. But we're going to change the value of x we're going to approach here. All right? In fact, we're going to do the same composition here for these three examples. F of g of x will be the composition that we're working with. All right, so let's start out with this first example here. It's asking me to find the limit of a composite function, which as soon as you see that, you should be thinking about that property we just looked at and see, does that property or that theorem apply here? So that's where we're going to start with this. There's two conditions that you have to meet. So let's check our first condition. The first condition talked about the limit of the inside function. So we're going to take the limit as x goes to 1 of g of x. So as x goes to 1 of g of x. So we're going to just focus on g of x over there. And we're going to consider what's happening over here on g of x as we approach 1. So here's 1 on our graph. So that means I'm going to jump on this curve and I'm going to go for a ride here from the left side. Do the same thing from the right side, and the question is, am I approaching the same value there? And I think we can definitely say yes, we are approaching a value of 5. So here we can say that this limit is equal to 5. So we meet the first condition. The limit exists, and in this case it's equal to 5. The second condition, we talked about continuity of the outside function. So we have to ask ourselves this question: is f, our outside function, continuous at x equals 5? We're asking ourselves that question right there. And again, notice that we're using the limit that we just came up with in the first condition. That's the value we're looking for continuity at on the outside function. So it's not at x equals 1 that we want continuity. It's at 5 in this case that we want continuity. All right, so let's take a look at function f and see if we've got continuity at 5. So I look at what's happening at 5. Here's 5 right here. And so the definition of continuity talks about the limit existing, the function existing, and them being equal to each other. So the function definitely exists because there's a point right here. The limit as I come in from the left side and from the right side is approaching the same value there. So the limit exists. In fact, those are equal to each other. The function exists, the limit exists, and they're equal to each other. So we meet our definition of continuity. So the answer here is a big yes, which is good news for us because that makes this limit really easy to find. In fact, we can say thus or therefore, however you want to say that. I'll just say thus. Our conclusion is that the limit as x goes to 1 of this composition, f of g of x, is equal to f of, and we evaluate it at the limit of the inside function. The inside function had a limit of 5, so I just have to find out what f of 5 is equal to. So if we scroll up here and look at function f, as I approach 5, it looks like, not approaching 5, what is the function at 5? And it's 2. That right there is our limit. Again, if I meet the two conditions there, that theorem is a very nice way to do this. All right, what happens if that is not the case? So let's take a look at example 2. Same two functions, f and g of x, but this time we're going to let x go to 5. All right, I've already kind of spoiled it, I guess, a little bit by saying that the limit theorem is not going to apply, but again, that's the place you'd start, is by checking to see if it applies. So again, start out with the limit as x goes to 5 of the inside function. So if I look at the inside function, g of x, and what's happening at 5, so here's 5. Again, if I jump on the curve and go for a ride here, as I approach from the left side and the right side, it looks like in both cases I'm approaching a value of 2. So the answer there is yes, the limit exists, and it is equal to 2. All right, so we meet the first condition. If I meet the first condition, I can continue on and check the second. Obviously, if I don't meet the first condition, there's no reason to check the second, because I already know that I'm not going to be able to use the theorem at that point. But I met the first condition, so now the second condition is to check continuity. Continuity of the outside function. Is f continuous at x equals 2? is the question we've got to ask ourselves. Do we have continuity at x equals 2? And again, I'll point out to you that we're using the limit we found in the first condition as the point that we're checking continuity at. I'm not checking continuity at x equals 5, but rather x equals 2. Let's take a look at function f at x equals 2. So here's 2. If I look at what our graph is doing, oh, we got a problem here, right? We've got a step discontinuity there. So no, the limit doesn't exist there, which means that we don't have continuity. So this is a big no. And with that being no, that means I cannot use the conclusion of this theorem. I can't just simply take f and evaluate it at 2 and get an answer. All right, so this is what that note was referring to at the bottom. And instead what we've got to do is we've got to consider one-sided limits. Now, it turns out you could always just consider one-sided limits, but you're going to see here that's going to take a little bit more work to do this. And that's the reason why checking for that theorem to begin with can simplify this for you. If we meet both conditions, we can apply that theorem, but here we can't. All right, so let's start out with the left-hand side. We're going to take the limit as x goes to 5 from the left-hand side of just the inside function. Notice I'm working with just the inside function, just like I did up above with that theorem. And I started out with just the limit of the inside function, but I'm doing it from a one-sided perspective here now. Now, we already kind of looked at this with that first step of that theorem, or first condition. But if I look at my function there, and I approach from the left side, I'll just mark a couple of points here to help us see what's going on. But as I approach from the left side there, I can see that I'm heading towards this value of 2, but I'm getting values that are slightly bigger than 2. As I approach from the left side, I'm at 2.5, and I'm at maybe 2.25, and then 2.1. I'm getting closer and closer to 2, but as I approach from the left side, I'm working with numbers that are slightly bigger than 2. So the way that we indicate that with one-sided limits is I'm going to use an arrow here. So I'm approaching this value of 2, but I'm working with values of 2 that are slightly bigger than 2. So the way we indicate that is with that little plus sign there. Remember, that little plus sign means that you're talking about numbers to the right of 2. Numbers to the right of 2 on your number line are numbers that are bigger than 2. So I'll use an arrow there and a 2 with a little plus as a superscript to indicate that I'm approaching 2, but it's from the positive side of 2, from the right side of 2. Now I do that because there's another limit I have to consider. The second limit I've got to consider is the limit as x goes to, and now the value I'm going to approach is the result of this limit here. I'm approaching 2 from the positive side. But now it's for the outside function. Again, notice that I'm taking this limit that I came up with here, and that is being used as the value of x that I'm approaching here. All right, so let's see what happens in this case. If I approach 2 from the positive side, that's 2 from the right side. So when I look at my curve here, I'm talking about jumping on the curve here and going from a ride here from the right side. Looks like I'm approaching a value of 4. So this is a limit of 4 is what we'd say. So what that tells me is that if I take the limit as x goes to 2 from the left side, limit as x goes to 5 from the left side, that my limit is 4. My conclusion from this is to say, thus, the limit as x goes to 5 from the left side of f of g of x is 4. All right. Now that's only one half of the story. It's a one-sided limit. So let's take a look at what's happening on the other side. Obviously, I want the limit from the left side and the right side to be the same, and then that will be my limit. Or if they're different, then the limit won't exist. But I've got to consider both sides here. So now let's consider the right side. The limit as x goes to 5 from the right side of g of x. And again, consider what's happening there on our graph. So if I mark a few points here again, just to kind of illustrate what's happening here. As I jump on the curve and go for a ride here from the right side, again, I'm up here at 2.5 maybe, and then I'm at 2.25, and then maybe 2.1. I keep getting closer and closer to 2, but it's numbers that are slightly bigger than 2. So the way that we're going to consider that is, again, we're going to use a little arrow here to indicate we're approaching 2, but I'm approaching a value of 2 from the right side or from the positive side. We're working with numbers that are bigger than 1 or bigger than 2 as we look at that limit. And again, I'm using an arrow to indicate that I'm approaching that value because there's a second limit I've got to consider. And the second limit I've got to consider now is the limit as x goes to the result of that first limit. So that's 2 from the positive side of f of x. Again, notice that you're using the result of this limit right here to help you determine the limit of the outside function. That's the value of x we're going to approach. Well, actually, we've already done that, right? I mean, I already saw over here on the left side that the limit as x goes to 2 from the positive side of 2 is 4. But if you want to look at the graph again, you can do that. You can look at the graph and say, yeah, as I approach from the right side of 2, I'm approaching that same value of 4. So this is equal to 4. So again, the conclusion from this work here is I can say that the limit as x goes to 5 from the right side of f of x, f of g of x, is equal to 4. Those are the two pieces that I use to figure out what's the limit as x goes to 5. The limit from the left side was 4, and the limit from the right side was 4. I can now put those two pieces together and conclude the following. I guess I'll say therefore, but you could say thus. Therefore, the limit as x goes to 5 of f of g of x is equal to 4. And again, this guy right here, I'm making that conclusion from looking at what's happening on the right side, what's happening on the left side. Since they were the same, I can now conclude that the limit was 4. Again, compare this work that we just did here with the first example. It definitely took a little bit more work to deal with this in terms of one-sided limits. But I could have answered example 1 just like this. I could have done this exact same work to figure out the first example. But that theorem is nice because it allows me to quickly jump to an answer. All right, let's take a look at another example here. A slight variation to this one. But this time, we're going to approach 3. Same two functions, f of x and g of x here. Same composition, f of g of x. And again, I've already kind of indicated that we're not going to be able to use the theorem here. But let's start with that, because that definitely is a lot faster solution here. So naturally, the way to start this is to say, what's the limit as x goes to 3 of the inside function? Does that limit exist? And what is it? So if I approach 3, here's our value of 3. If we jump on the curve on the left side and go for a ride, same on the right side, it looks like we are, in fact, approaching the same value. In fact, it looks like it's always the same value. It's 1, right? The limit is 1. And now, the second condition is we got to check for continuity. Is f continuous at x equals 1? And again, just to remind you of this again, we're looking at the limit from the condition, the first condition. We're using that to figure out, do we have continuity as we approach that point there on the outside function. Okay, so let's see what's happening at 1. So here's 1. And we got to have continuity. No, we got a problem here. We got actually a removal of this continuity here. So that's definitely an issue. So it looks like the answer to our question here of do we meet both conditions is no, because we don't have continuity. So therefore, I can't use the theorem. So instead, we're going to have to again jump to one-sided limits. So let's take a look at our one-sided limits. Okay, and I'm going to start on the left side, and then we'll deal with the right side in a second. So we're talking about the limit as x goes to 3 from the left side. And again, it's of the inside function. Start with the inside function and work your way out. All right, so what's happening as we approach 3 from the left side? All right, so if I jump on this curve on the left side of 3, and I go for a ride, like right here at 2.5, I'm actually getting a y value of 1. And here at 2.75, it's still a y value of 1. And 2.9, still a y value of 1. It looks like I'm always 1. I'm not sometimes bigger than 1 or sometimes less than 1. It's always 1. That's all I get. It's not bigger values bigger than 1 or values smaller than 1. It's exactly 1. So for that reason, because that function is a horizontal line there, I'm not going to use an arrow here. I'm going to say that this is exactly equal to 1. I'm always getting a value of 1. Now, because of that fact that I'm not approaching 1 from above or below, that means that when I go to do this next part, I can actually just evaluate my function at that given point. So I can take my outside function and I can evaluate it at that given value of x, or y that we're approaching there, which is 1. Again, I'm taking the result of this limit here, and in this case it's exactly 1 as I approach, and I'm using that as my value that I'm plugging into my function. Notice it's not a limit I'm finding this time. I can just simply evaluate my function there. And what's my function at 1? Well, if I go back up to my graph, it looks like that when I plug in 1 into this function, here's the point that I'm defined at. So it looks like I'm going to get a value of 3. So f of 1 is equal to 3. So my conclusion from this, for the left side of this, I can say thus, the limit as x goes to 3 from the left side of f of g of x is equal to 3. All right, that's only half the story. I still got to consider what's happening on the other side of 3. So let's take the limit as x goes to 3 from the right side of the inside function again. Again, let's go back to our graph. Again, you'll notice your graph is a horizontal line. It's a constant function there. So this is, again, a special situation here because now as I approach 3 from the right side, you know, here at 3.5, I get a y value of 1. At 3.25, I get a y value of 1. At 3.1, I'm getting a value of 1. Everywhere I look there, I'm always getting a value of 1. So again, the limit is not approaching 1 from above or approaching 1 from below. It's always 1. So I can say that this is equal to 1. And so because of the fact that it's equal to 1, I can again evaluate my outside function at that value. Again, I'm taking the result of that limit here. I'm using that as my input into my function f. But again, because of the fact that function g is a horizontal line at that point, this is the reason why I can just plug in that value. Now we've already evaluated f at 1, but again, if you look at your graph, I'm looking for the filled in circle there. So at x equals 1, I'm getting a value of 3. So this is equal to 3. And so my conclusion from this is thus the limit as x goes to 3 from the right side of f of g of x, my composition, that's equal to 3. And so those are the two things I'm considering now. I'm looking at the limit as x goes to 3 from the left side, looking at the limit as x goes to 3 from the right side for this composition. If those are the same, then that's my limit. If they're different, then my limit does not exist. So we can say, therefore, from this work, we have that the limit as x goes to 3, the two-sided limit of f of g of x, this is equal to 3. And again, I'm making that conclusion right there about this limit by considering what's happening on the right side, by considering what's happening on the left side, and using those two to help me get my answer. All right. Again, this scenario here was a little bit different than the previous example because of what my function g, the inside function, is doing as I approach 3. I have a horizontal line there. I've got a constant function, which means that I'm always getting the same value out of that function as doesn't matter how close I get to x equals 3, I get the same result out. Now, one thing you could do to help yourself understand this a little bit better might be to make a table of values here. Maybe I can do that up here. If I make a table of values, you don't necessarily have to do this, but if it helps you see or understand better why this is the case, consider making the following table here. We'll plug in some x values into function g, and then we'll take that result and plug it into function f. We'll just look at these three values here. So let's consider the left side just as an example. So if I pick a value that's to the left of 3, like let's pick 2.5. If I plug in 2.5 into my function g, I get a value of 1. Not close to 1, not slightly above or slightly below 1, but it's exactly 1. So now I could take that result and plug it into function f. If I plug in 1 into function f, what do I get? I get a value of 3. Let's repeat that. Let's get closer to x equals 3 from the left side. So let's make this 2.8. If I look at what's happening at 2.8 on this graph, again, function g is exactly equal to 1. Not above 1, not below 1, but exactly equal to 1. If I take that value of 1 and plug it into function f again, guess what? We get the exact same thing. We get a value of 3. And I can even get closer. What happens at 2.9? Same story. It's a y value of 1 that function g gives me. When I plug that value of 1 into function f, I get a value of 3 again. I can even get closer. You can keep going with this as long as you want, but guess what? You keep getting the exact same value of y from function g. And when you take that result and plug it into function f, you get the exact same result every single time from function f. You always get a value of 3. So as you can see, this composition, f of g of x here, this guy right here is always giving you a value of 3. That's precisely the reason why down below we saw when we considered the limit as x went to 3 from the left side, that we're getting a value of 3. You can do the same thing from the right side with the table. I'm not going to do that here, but if you wanted to see that you get the same result, go ahead and do so. If this helps you by making a table of values to help you see that limit, for any one of these 3 examples, go ahead and do so. That certainly can sometimes help you out there. Now, if your function is not constant there, then you might have to kind of approximate some values, but they'll still be close enough. And then you can plug them into your outside function and see what happens at those values. All right, again, approximations will definitely still be better than nothing if you're struggling with the this idea here. Use a table sometimes to help. All right, that right there is the end of section 2-4.